all yours.
Thank you very much for the kind introduction. Pleasure to be here with you today and talk a bit about our activities in hybrid photonic integration and the versatility of hybrid photonic integration technologies for various applications. So as I'm the first speaker of today, Dimitri has asked me, Ivan has asked me to introduce some aspects of photonic integration, hybrid photonic integration, to get everybody here in the workshop up to speed of what we are talking about. So that's why I just added 2 slides to my talk just today. Well, I'm sure that everyone is aware that in photonic integration, we want to integrate lots of optical functionalities from bulk optics into miniaturized chips. For example, lasers, detectors, waveguides, filters, in order to provide multi-purpose photonic integration platforms that can cater for a broad array of applications. For example, transmitters for communications, readout units for sensors, photon sources for quantum technologies, and the like. There are several integration techniques that are being employed. One, of course, is monolithic integration, where the actives and the waveguides are on the same die. So everything has to be fabricated in a semiconductor material system, mostly indium phosphide, because it has a band gap that is suitable for near-infrared light emission detection. One great advantage is that once you have fabricated your chip, you have your optical subassembly, so you do not need to do any assembly at this stage, just some module packaging, fiber coupling, that's it. However, you're intrinsically limited by the properties of the material. For example, if you want to go to shorter wavelengths, for example, indivisible, we want to fabricate a laser that emits indivisible, a tunable laser, then this material would be out of question. So if you want to go to other wavelength regions using a monolithic integration approach, you have to do all the development all over. And the second thing that you need to take into account in monolithic integration is that even though you might be able to fabricate, for example, lasers and detectors and modulators and waveguides on a single chip, there usually are some trade-offs in the manufacturing between all these different components. So usually the specifications that you get from these elements on a monolithic integrated circuit are not as high as you would get from components that are fabricated on dedicated wafer runs. For example, dedicated lasers, dedicated modulators, dedicated detectors. In hybrid photonic integration, on the other hand, waveguides and actives are fabricated on separate dies. So actives, again, usually semiconductors. These can be indium phosphide, for example, for lasers, but can also be gallium arsenide for lasers shorter wavelength, or silicon detectors, coupled to passive waveguides, for example, in silicon nitride, polymers, thin film lithium niobate, and nonlinear optical elements, for example, periodically fold lithium niobate and KTP. Here on the top are some examples from recent hybrid photonic integrated circuits, one from HHI. Then we have here a hybrid laser from Lyonics, and I am sure that Dimitri will talk a bit more today about hybrid lasers. And here one recent example from EPFL with a laser at shorter wavelength. And for these hybrid integrated circuits, obviously you need to assemble the different dies. You can do this via butt coupling. You can do this, for example, also via microtransfer printing that we will probably hear more about in the upcoming talk. But you have the advantage that you can combine the optical components and novel functionalities on a single chip without having to redevelop everything from scratch once something changes. And also you have advantages in terms of yield management, because this hybrid integration approach allows for the use of known good dies that can be combined onto a single PIC. So these were the two general introductory slides that I wanted to present. And with that, I would like to go into some more details of what we are doing at HHI in terms of hybrid photonic integration. So what we do is we combine single components, semiconductor components such as lasers, detectors, modulators, single photon detectors, and passive waveguiding platforms, as I've shown you before. But what we also do is we integrate there micro-optical bench approaches, micro-optical elements such as isolators, thin film filters, crystals, and lenses. And this I want to introduce briefly to you today. Just a quick overview of what the waveguiding layer looks like. This is based on polymer materials that are commercially available, fabricated on 4-inch, 6-inch wafer scale. We have the scaling to 8-inch on the roadmap. We use single mode waveguides with rather low refractive index contrast, and we can just dice the chips, and no coating and polishing is required because the refractive index of the waveguides is quite close to the refractive index of the standard single mode fibers. And here we have one example of a hybrid integrated functionality on these chips. In this case, a tunable laser, where we have an indium phosphide element here that is HR coated on the backside and anti-reflective coated on the coupling interface that is coupled, butt-joint coupled towards a polymer-based chip with a waveguide where we have an inscribed Bragg grating. And this Bragg grating acts as the second mirror for the laser cavity, and it is tunable by means of thermo-optical tuning. And in this way, we were able to realize tunable C-band lasers, but the same approach can be used for shorter wavelength. So this is one of the beauties of the hybrid integration concept. So we leave everything as is, adapt the parameters here a bit, exchange the gain chip, and in this way we can realize tunable lasers for 1064 nanometers and for 785 nanometers using other gain elements. And these lasers are then building blocks that can be used to fabricate more complex photonic integrated circuits, for example, for sensing, for communications, and for quantum technologies. One other functionality that I briefly want to introduce is the use of thin film elements. So despite having optical filtering functionalities that is waveguide integrated as is usual in photonic integration, we also have the possibility to use these thin film elements. These are basically very thin dielectric layer stacks, as you know them from classical optics, where you have coated lenses, dichroic mirrors, and the like. And in this way, we are able to transfer efficient filter characteristics from free space into integrated optics on a small footprint and in a temperature-insensitive manner. Here's one example shown for polarization beam splitter that is quite effective with more than 40 dBs of polarization extinction ratio and low insertion loss of below 0.7 dBs from fiber to fiber. Here, one example from quantum technologies, where we have a filter that suppresses the pump light by more than 60 ATBs in the waveguide on the integrated chip, which is very important for the generation of single photons and photon pairs. And a third building block on the chip that we use extensively is our micro-optical elements, where we have graded index lenses, so short pieces of graded index fiber that we polish to an exact length to act as a collimating or focusing lens that are inserted into the PIC itself in order to realize free space sections on the chip, where we can insert basically whatever we like. For example, isolators, as here, with lower than 1 dB on-chip loss in forward transmission and more than 40 dB peak isolation. Another thing that we can integrate using this approach are periodic fold crystals for nonlinear optics. And yeah, with this, I already come to some examples that I want to show to you today. One example here from communications as a photonic engine for transceivers. This is part of the terrific EU project, where we have waveguide ratings as the multiplex and demultiplex functional building blocks on the chip. And these are used to couple arrays of externally modulated lasers and waveguide photodiodes in order to realize transceivers for next generation data centers. And here, one example with H-channel photodetectors and H-channel EML arrays demonstrating 800 gigabit per second capability. And in the next step, we realized a 16-channel transceiver, again, using the same building blocks that we developed for the smaller versions, using a bigger polyboard chip. And yeah, this is also one great advantage of the hybrid photonic integration technique, is that you can have the active elements where you need them. Here you see these small arrays of active elements and this big chip with just the passive waveguides, which gives you a great cost advantage compared to monolithic integration for these kinds of applications. And of course, you need to also assemble it. And this is something that we are also automatizing together with partners, in this case with Ficontech, where we have automatic contacting of the arrays, automatic fiber insertion here into the chip, active alignment of the EMLs that you see here. Same being done for the photodiode arrays that are also actively coupled to the chip, cured, and then you have the optical subassembly. So this is also one important thing that you need to always take into account in hybrid photonic integration. Here, another example from a European project, Terahertz, which is for microwave communications. So this is a hybrid photonic integrated chip that generates microwave radiation for example, 6G networks. Here again, we have these tunable lasers that are introduced. We have the optical isolator on the chip, a quite unique functionality. We have a modulator PIC from indium phosphide, an antenna PIC from indium phosphide, and then finally a triplex PIC from silicon nitride from Lyonics. And I mean, even though you see here various indium phosphide PICs, these are all optimized for their respective functionality. So these modulators are optimized for modulation. The antennas and photodiodes are optimized for their functionality, and the gain shifts are optimized to generate photons. So again, underscoring the advantage of hybrid photonic integration for these kind of very complex integrations. And one last example here from quantum technologies. Here we make use of The micro-optical bench, where we insert quite a large periodically cold KTP crystal that generates photon pairs from an input of 775 nanometers, generating photon pairs at 1550 nanometers with orthogonal polarization that are split by these polarizing beam splitter that I introduced earlier. And the pump light is suppressed by the thin film element with more than 60 dB suppression on the chip. And indeed, we can demonstrate photon pair generations using this approach in a hybrid photonic integrated way. And these photon pairs are then available for more complex processing in the waveguide on photonic integrated circuits. And yeah, with this, I'm already at the end of my talk, and I'm looking forward to your questions.